Good morning everyone. I, Rajni Prashar, welcomes you all to the video lecture series of VLSI technology course with the subject code KEC 053 under the AKTU syllabus scheme. This is the second lecture for this course VLSI technology, and the topic of today's lecture is crystal growth techniques. So in the previous lecture we got to know about the integration of IC technology, that how the ICs can be classified into n number of segments, that is SSI to VLSI and up to ULSI chips, depending upon the number of components, number of transistors which we can fabricate on a single wafer. And second thing we got to learn in the first lecture is the crystal structure of silicon. We are now familiar with the structure of silicon and what are the common defects and dislocations which are possible to be in a single crystal. And we know that the starting material for any IC fabrication is the silicon wafer, that is a single crystal wafer. So single crystal silicon must be grown. In today's lecture we are going to learn that how that single crystal wafer is grown. We know that silicon is one of the abundant material in the nature and it is found in the form of silicon dioxide. It is found in the form of silicon dioxide. So first, this silicon dioxide is reduced in order to obtain the silicon. It is purified further in order to get a very high purity silicon grade silicon, and that is pure up to 99.99% purity. And once this highly pure silicon grade silicon is extracted, we can use it as a starting material to obtain the silicon ingot, and that silicon ingot will be then sliced into the wafers on which we can fabricate the number of transistors. So in case of crystal growth, the basic material, the electronic grade silicon, it is a polycrystalline material of high purity and is the starting material for the preparation of single crystal silicon. This EGS is made from the metallurgical grade silicon, MGS, that is commonly known as MGS material, which in turn is made from the quartzite, which is relatively the pure form of sand, which is very much abundant in nature. And this MGS is purified by the following equation, that is written as silicon, when it is reacted with hydrochloric acid, it will give you trichlorosilane and hydrogen, and some heat will be generated as a residual. So the boiling point of this trichlorosilane gas, its boiling point is 32 degrees C, and that can be readily purified using the fractional distillation. This EGS is formed by reacting the trichlorosilane with the hydrogen. So in the second equation we can see that this trichlorosilane gas is reacted with the hydrogen gas, so that we can have a solid form of silicon which is pure and free from the impurities, and HCl gas, hydrochloric gas, as a residual. So this polysilicon has typical contamination level of less than 0.001 particle per billion, and this crystal growth method provide a very highly pure silicon which is 99.99% pure. So basically there are two techniques which are commonly used for the crystal growth. The first one is the Bridgman method. In this method has a very simple process, but has a lots of defect and dislocations in the resultant crystal. And this Bridgman method can be classified into two parts. One is horizontal Bridgman technique and the second one is vertical gradient freeze technique. The second most popular method, that is known as Czochralski method, it is also known as CZ method, and most of the silicon wafers that we are using today for the IC fabrication technology is grown with the help of this Czochralski method. This CZ method of crystal grown is usually much more complicated system as compared to the Bridgman method, on one side where the Bridgman method has so many drawbacks that we have less control parameters in our hand to control. Because of that we have so many dislocations and defects in case of Bridgman method, but in case of CZ method, it is a complicated method, and there are so many parameters are there to control in CZ method, but the resultant crystal has much more less dislocations and defect. So these days this Czochralski method is most commonly preferred for the growth of this single crystalline wafer or single crystalline ingot, we can better say, because we have to make a cylindrical ingot, and that will be cut into slices, so that slices will be further used for the wafer for the IC fabrication technology. This CZ method is also known as liquid solid monocompound growth system. In CZ method, we have basically 4 subsystems. First one is furnace, then crystal pulling mechanism, then ambient control, and the control system. This is the vectorial diagram, the machine which is used in the foundries to grow the silicon ingot. This is the silicon ingot which is grown as a result with the help of this Czochralski crystal furnace. And this is the diagram which we are going to study and which we are going to draw in this course. So in this Czochralski crystal furnace, we have this seed holder which is used to hold the seed. So in case of CZ crystal furnace, this is the pictorial diagram which is used in the foundry to generate this single crystal ingot, silicon ingot, that is cut into slices. This kind of silicon ingot is generated, and which is cut into then slices, and that again will be partitioned into n number of segments, and on each segment one IC can be fabricated. So to generate this silicon ingot, we have this seed, quartz crucible will be there, water coolant chamber will be there, heat shield will be there, carbon heater, graphite crucible support, spill tray, and some electrodes will be there. Now come to this diagram, which is very much easy to understand. So in this diagram we have the seed holder. This is the same diagram, another pictorial representation of this furnace. This is the seed holder which is used to hold the seed here. Here we can see that we have some silicon seed, which is the pure silicon seed, single crystal seed, which is used as a starting material to generate the silicon ingot. Then crystal neck will be there, shoulder cone, single crystal silicon which is generated with the help of this process. Then we have these thermal shields, heaters, some RF heaters will be used so that heating process can be continued, crucible susceptor, crucible, silicon melt, and crucible shaft. Now let us get to know about each part of this silicon furnace. The first one is the seed holder. This seed holder shaft is used to hold the seed. Okay, your silicon seed will be connected to this shaft, which can be lifted up down. This shaft can be lifted up and down, and it can be rotated simultaneously. We can rotate it in a clockwise direction and in a anti-clockwise direction. So at the end we have a small seed crystal, which is the pure silicon, or we can say electronic grade silicon, EGS, or single crystal. The second one is the crucible. Crucible is also known as graphite cup. This first one is the seed crystal, and the second one, this is the crucible. This crucible is also known as graphite cup, in which we have the melted form of EGS. Now this EGS can be of N type and P type, depending upon our requirement that what type of silicon ingot we want to generate. Depending upon that, your impurities will be added to this silicon, and its melting point should be very high. Next we have the crucible susceptor. it is used to support the crucible so that the graphite cup will remain stable throughout the process. Next we have this crucible shaft, okay. This shaft is used for the movement left right only. We cannot use that shaft for the upside and downside movement, okay. And the one very much important thing should be kept in mind that this shaft, this rotation, if we are using it in an anti-clockwise, this should be in clockwise direction. This should be in clockwise direction. The very basic phenomena behind that is the screw and nut example. If we rotate both the sides simultaneously, the separation will be easily and quickly done. Instead of that, the rotation is done on a single side. So for that purpose, these rotations are done in opposite direction. If we are using it in anti-clockwise direction, we have to rotate this in a clockwise direction. Next is the ambient gas inlet. In this furnace, we must have some input gas and some gases will be exhausted out. Okay. So before starting the process, all the gases which are present in the chamber will be exhausted out and some of the gases will be inserted in. Obviously, we cannot, this process cannot be done under the presence of oxygen, because oxygen may react with the silicon and form the silicon dioxide. So argon is passed in the chamber and it is an inert gas which neither react with the silicon nor allow the other gases to react with the silicon. So inert gas argon is used to pass in the chamber so that the resultant silicon ingot will be free from any contamination. Next we have some gas outlets will be there, which is used to exhaust the extra gases. Next, in this system it must have some, it will definitely have some temperature sensor which is used to check the temperature throughout the process. Then we have the control system which also contains the power supply for the continuous power supply throughout the process, and this control system is used to control the temperature and shaft movement and lift movement also. Then we have the RF heater which is used to melt the silicon, because this silicon is in melted state. So this silicon is melted with the help of RF heaters. So let us get to know that how this process is done. So when a seed crystal is attached here, that seed crystal is pulled down in the melted silicon and it will be pulled up within a fraction of second, and which will generate a layer of silicon, single crystal silicon on the seed. Okay, and with the help of that repetition process we have this resultant. Now the pull-up mechanism in this process is very much important, that we will see in the next slides. So in this CZ method, this process uses the Czochralski crystal grower. Poly EGS is melted in quartz lined crucible at about 1412 degrees C. Seed crystal is introduced into the molten poly EGS to begin crystallization. Seed is pulled slowly, allowing the crystal to grow on it. Simultaneously, this crystal is rotated slowly to give the side steering of the melting of the melt to prevent the inhomogeneous solidification. Then ingot is cooled at a very slow rate. In this diagram, we can see that this seed is pulled down in the liquid. This is the liquid. okay, and here we have the seed, and that seed is pulled down in the liquid and it is simultaneously rotated back in the upward direction, and with the simultaneously process, with the regular process, we have this silicon ingot as a resultant. So this technique is widely used in growing silicon, germanium and some another compounds in semiconductor. This process transforms the polycrystalline silicon into samples with a singular cluster orientation, which is known as ingots. The polysilicon is mechanically broken into 1 to 3 inch chunks and undergoes surface etching and cleaning in a clean room environment. These chunks are then packed into quartz crucible for melt down at 1420 degrees C in a CZ furnace. Then monocrystalline silicon seed is installed on a seed shaft in the upper chamber of the furnace. Slowly this seed is lowered so that it dips approximately 2 mm in the silicon melt. The seed is then slowly retraced from the surface, allowing the melt to solidify at the boundary. As the seed pulls the silicon from the melt, both the crucible and the seed are rotated in opposite direction, that I have explained in the pictorial diagram, in the opposite direction to allow for an almost round crystal to form. CZ furnaces also must be stable and isolated from the vibration. Once the proper crystal diameter is achieved, the seed lift is increased. This, along with the heat transfer from the heater elements which control the diameter of the crystal, and this gradual cooling allows the crystal lattice to stabilize and makes the handling easier before transport to the next operation, that is slicing of the wafer into slicing of the ingot into wafers. So what should be the pull up or pull down rate of the seed? So if the pull up rate as well as the thermal conditions are not carefully adjusted, the reverse can also happen. The seed can also get melted if we put that seed more than the desired time, and the pull rate should be adjusted very carefully, and if you draw it too fast, you may not get a single crystal, right? So the pull up mechanism and the time during which it should be dipped in the liquid, it should be monitored carefully. If you draw it too slow, you may even get the seed crystal melted. So this equation is used to decide that what would be the pull up rate. In this equation, we have this L dm by dt plus KL dt by dx1 A1 is equal to Ks dt by dx2 A2. This is just a heat transfer equation where L is the latent heat of solidification, dm by dt is the mass solidification rate, KL is the thermal conductivity of liquid, Ks is the thermal conductivity of solid, dt by dx1 is the thermal gradient in the melt, dt by dx2 is the thermal gradient in the solid, that is in the form of crystal. A1 and A2 are the area of the isotherms in the melt and in the solid. So at the thermal equilibrium condition with some assumption, we will have this resultant equation, that dx by dt is equal to Ks dt by dx2 Lx rho. This is the maximum attainable pull up rate. This equation will give you the maximum attainable pull rate, and this maximum attainable pull rate, that is when I can assume that the thermal gradient in the melt is going to be 0. In practice, the pull rate is kept less than the maximum pull rate, and in practical the system, what happens is there will be a small change in the temperature of the melt. That is why it is kept slightly less than the maximum pull rate, because we are pulling out the crystal, the thermal condition, their thermal conditions are continuously changing. So in practical system, actually we should use the feedback system. The control systems are used, which is used to control the parameters, that is used to control the temperature so that the cooling can be done properly. That feedback is used to control the heat to the melt also, so that the temperature is maintained within plus minus 0.5 degrees C. So, and now we can understand that this heat loss, because of that heat loss, the heat needed to be supplied in the system, and that extra heat, that extra heat that is supplied to the system is done with the help of that control system only. Next is impurity segregation, that how many what types of impurities are present in the silicon ingot. Impurities, both intentional and unintentional, are introduced into the silicon ingot. Intentional dopants are mixed into the melt during the crystal growth, that what type of silicon ingot we want, whether we want the N type material or we want P type material, right? While the unintentional impurities are originate from the crucible and the ambient of the furnace. So, all common impurities have different solubilities in liquid and in melt. An equilibrium segregation coefficient K0, this K0 can be defined to be the ratio of the equilibrium concentration of impurity in the solid to the liquid, right. So, this K0, equilibrium segregation coefficient K0, can be defined as the concentration of impurity in the solid divided by concentration of impurity in the liquid. And in this table we can see that all the values are below unity, which implies that the impurities segregate into the melt and the melt become progressively enriched with the impurities as the crystal is being pulled. The impurities will be segregated in the melt easily, and as a resultant that impurities will be easily passed to the silicon ingot. So, we can see from the table that the impurity and their equilibrium segregation coefficient for aluminum, arsenic, boron, carbon, copper, iron, argon, phosphorus and antimony, they have the equilibrium segregation coefficient K0, the value which is less than unity. Then this impurity distribution, the distribution of impurity in the grown crystal can be described mathematically by the normal freezing relation, that is Cs is equal to K0 C0 1 minus x raised to the power K0 minus 1, where x is the fraction of the melt or solidified, C0 is the initial melt concentration, Cs is the solid concentration, K0 is the segregation coefficient. In this slide, we will get to know that what will be the weight of the ingot when we apply some, when we dope some impurities in that, what will be the initial weight and what will be the resultant weight after that. So, consider a crystal being grown from a melt having an initial weight M0 with the initial dopant concentration C0 in the melt, okay. And at a given point of growth, when the crystal of weight M has been grown, the amount of dopant remaining in the melt is represented by its weight S. Okay, S is the dopant remaining in the melt, that how much dopants are remained in the melt after the silicon ingot is start generating. So, for an incremental amount of crystal with the weight Tm, the corresponding reduction of the dopant will be there. Obviously, if your silicon ingot with the weight Dm it started to form, some of the dopant will be reduced, that is given by minus of ds from the melt Cs Dm, where the Cs is the dopant concentration, of the crystal with the weight minus ds is equal to Cs Dm. So, by using this equation, by solving this equation, we can have this Cs is equal to K0 C0 1 minus m by m0 k raised to the power minus 1, where m is at any given point when the crystal is grown, m0 is the initial weight, C0 is the initial dopant concentration and Cs is the dopant concentration in solid. So, this is the graph of the impurity concentration profile of the silicon ingot with different values of K0 and C0 is equal to 1. and this is the oxygen concentration in the silicon ingot, that how this oxygen is present in the crucible. So, oxygen in silicon, this oxygen in silicon forms a thermal donor in silicon. This oxygen increases the mechanical strength of the silicon, and oxygen precipitates provide getting the sites for the unintentional impurities. Okay. Then we have the thermal donors. Thermal donors are performed by the polymerization of silicon and oxygen into the complex such as monosilicate in interstitial sites at very high temperature, that is 400 degree C to 500 degree C, and the careful quenching of the crystal annihilate these donors. So, this is all for today. In today's lecture, we will get to know about the CZ method of the crystal grown technique, that how silicon ingots are generated and what is the pull up mechanism, what should be the pull up rate of the shaft, that a proper silicon ingot can be generated, and that silicon ingot will be further used for the next process. Thank you so much.